Jupiter seems like the obvious grand destination after Mars, until you ask where a human crew could safely go. Then the plans begin backing away from the planet before the spacecraft has even left Earth. Mars gives you a surface. It has ground beneath your boots, sunlight for power, and a day close to our own. Jupiter offers none of that. The planet is mostly hydrogen and helium, with no solid surface waiting below the clouds. Descend far enough, and the growing pressure would crush a spacecraft long before it found anything like land. Even staying above Jupiter brings another problem. The planet has an enormous magnetic field that traps charged particles and drives them around at high speed. For a crew, that creates intense radiation. Electronics need protection. Human bodies need much more. A mission lasting months or years cannot treat that exposure like a brief medical scan. So serious human mission studies often shift the destination outward. The crew might visit Jupiter's moons, or remain far from the planet while robots travel closer. Callisto, the outermost of Jupiter's 4 large moons, has attracted attention partly because the radiation there is much lower than around Europa or Io. That is a strange kind of retreat. You cross hundreds of millions of miles, reach the Jupiter system, and still keep the giant planet at a careful distance. This changes what a human trip to Jupiter means. It would not be a landing on Jupiter at all. It would be a long expedition through its surrounding system, with the planet acting less like a destination than a powerful hazard at the center. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. A map of the solar system can make the planets look like stops on a railway line. Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Each one sits a little farther along, so the natural thought is that each trip simply takes a little longer. That works well enough on paper. It fails as soon as you have to build the spacecraft. Suppose you're planning a drive across town. A longer route means more fuel and perhaps an earlier start. Stretch that drive across a continent, though, and the car alone is no longer the plan. You need places to sleep, food, repairs, weather forecasts, and some idea of what happens if the road closes behind you. Space travel crosses the same kind of boundary. Distance grows steadily on a map, but the problems don't grow steadily with it. Mars is already far enough to be difficult. Depending on the route, a one-way flight takes months. Radio messages also need minutes to cross the gap. That delay rules out anything like a normal phone call, but Earth can still answer within the same part of your day. Solar panels still receive a workable amount of sunlight. A damaged system has to last, yet the mission may still be counted in months or a few years. Now move outward. Jupiter orbits about 5 times farther from the Sun than Earth does. Saturn lies nearly twice as far out as Jupiter. Uranus is roughly twice as far again, and Neptune is farther still. Those distances are not a schedule with extra pages added at the end. Sunlight weakens with the square of the distance. At Jupiter, a panel receives only about 1/25th of the sunlight it would receive near Earth. At Saturn, it gets roughly 1/90th. By Neptune, the share is about 1/900th. You can build larger panels, choose another power source, or reduce what the spacecraft consumes. None of those choices is free. The travel time changes the machine as well. Parts must survive cold, vibration, and years of steady wear without a mechanic nearby. Software has to manage faults while instructions are still crossing space. At Neptune, a radio signal takes about 4 hours to reach Earth. A reply needs another 4 hours to return. Even perfect controllers are working across an 8-hour conversation. That alters how you design almost everything. A minor failure during a nearby mission might be studied by a room full of engineers before the next decision. Farther out, the spacecraft may have to protect itself first and explain what happened later. It needs enough stored power, enough spare capacity, and enough independence to remain safe while Earth is still learning there's a problem. There's a slightly absurd human consequence here. The people who begin a mission may not be the people running it when the spacecraft arrives. teams retire, computers on Earth are replaced, file formats age, a project must carry its knowledge through time as carefully as the spacecraft carries fuel. So the tidy ladder has a hidden break in it. Beyond that break, the destination isn't merely farther away. The whole mission belongs to another engineering category. Where, exactly, does that break begin? You can see the break in a place where mission planners rarely make speeches about it: the destination box. When engineers study sending people toward Jupiter, they usually don't place the crew beside Jupiter. They move them outward toward Callisto. That choice can seem strange at first. Jupiter is the great prize. It's the largest planet, with violent storms, an enormous magnetic field, and moons that may hide oceans beneath their ice. If people are going all that way, Callisto can sound like the seat in the back row. But the back row is chosen for a reason. In 2003, a NASA study called Human Outer Planets Exploration examined what a crewed journey into the Jupiter system might require. Its reference destination was Callisto, the outermost of Jupiter's 4 large moons. The study didn't choose the moon because it was the most scientifically exciting place nearby. Europa's buried ocean had already made it one of the most compelling targets in the solar system. Callisto was chosen because a crew might have a better chance of living there. Jupiter's magnetic field traps charged particles and drives them around the planet. Near the inner large moons, those particles create intense radiation. A spacecraft can carry shielding, of course. You use the same basic idea at a dentist's office, when a heavy apron is placed over you before an X-ray. Put enough material between a person and the radiation, and less reaches the body. The trouble is that shielding has mass. More mass means a larger vehicle, more propulsion, and more work at every stage of the mission. Some radiation also produces secondary particles when it strikes the shield. So this isn't a problem you solve by wrapping the crew cabin in an arbitrarily thick shell. Callisto travels much farther from Jupiter than Europa does. It still sits inside Jupiter's magnetic domain, but it avoids the worst regions faced by the inner moons. That makes its surface a more plausible place for a human outpost. Robots could travel inward from there. People could study the system while keeping their own exposure lower. Notice what has happened. Before anyone has settled the design of the ship, the human destination has already backed away. The crew doesn't descend into Jupiter's clouds. It doesn't land beside Europa's fractured ice. It goes to the large moon where the radiation is less punishing, then sends machines closer. There's something wonderfully human about that compromise. We cross hundreds of millions of miles to visit Jupiter, then choose the moon with the safer parking space. Callisto is not safe in the everyday sense. The crew would still face radiation from space, low gravity, extreme cold, isolation, and no quick rescue from Earth. Yet the target choice shows how serious planning works. The danger isn't added later as a warning label. It changes where people are allowed to go. And if Jupiter's radiation can move the destination before the spacecraft even exists, what else must change before a crew can leave Earth? A flight to Jupiter begins with noise, pressure, and a rocket burning fuel at a startling rate. Then, within minutes, the main engines stop. Most of the trip becomes a long coast through space. Juno gives us a good measure of how long that coast can feel. NASA launched the spacecraft in August 2011. It reached Jupiter in July 2016. Nearly 5 years passed between those events. That's long enough for a child to start school. You could move homes, change jobs, wear out a laptop, and forget which songs were playing when the mission left Earth. Through all of that, the spacecraft keeps moving, day after day. There's no roadside scenery, and no nearby Jupiter growing steadily outside a passenger window. Juno didn't simply aim at Jupiter and fly straight there. Its rocket couldn't provide all the speed needed for that route. The spacecraft traveled beyond Earth, returned 2 years later, and swept past our planet for a gravity assist. Earth's motion around the Sun helped send Juno onward. It's a little like a slow cyclist catching a pull from a passing truck. except gravity does the work and nothing touches. The encounter changed Juno's speed by about 8,800 miles per hour. That's roughly 14,200 kilometers per hour. Even with that boost, years of travel remained. By arrival, Juno had covered about 1.7 billion miles, or 2.8 billion kilometers. That wasn't the distance between Earth and Jupiter. It was the length of Juno's curved route while both planets continued circling the Sun. For a machine, the waiting can look uneventful. It isn't. Juno's computers stayed active. Its solar panels kept gathering light. Engineers watched its health, corrected its path, and prepared commands across a growing delay. Near Jupiter, a radio message from Earth took tens of minutes to arrive. Any reply needed just as long to come back. A crew would have to live inside that same stretch of time. 5 birthdays could pass between the planets. Food, water, exercise, repairs, sleep, illness, boredom, and disagreements would all happen without a quick return home. The people aboard would watch Earth shrink from a world into a bright point. Launch day would become an old memory, while Jupiter remained somewhere ahead. That's the more realistic shape of the trip. The rocket launch is brief. The coast is the mission, a small enclosed world working for years, with no roadside stop and no rescue vehicle close behind. Juno could be monitored and commanded from home. Its passengers would be instruments built to wait. But what changes when the cargo is awake, breathing and counting every day? New Horizons gives us the fastest famous version of this trip, and it still took more than a year. NASA launched the small probe in January 2006. It passed Jupiter in February 2007, about 13 months later. For a spacecraft crossing hundreds of millions of miles, that was remarkably fast. For a person waiting to arrive, 13 months would still be a very long ride. It sounds much better than Juno's 5-year cruise. But New Horizons wasn't arriving at Jupiter. It had no plan to slow down, enter orbit, or stay. Jupiter was a waypoint on the much longer trip to Pluto. A train can race through your station without stopping. That doesn't mean it can drop you off, support you there, and carry you home. New Horizons did the spaceflight version of racing through. The probe passed about 1.4 million miles above Jupiter's cloud tops. That's roughly 2.3 million kilometers. During the encounter, Jupiter's gravity bent its path and increased its speed toward Pluto. Engineers call this a gravity assist. The planet gave the probe a faster route outward. That worked because New Horizons only had to survive the pass. It didn't need enough fuel to break into orbit. It didn't need a habitat, radiation shelter, food, water, medical supplies, or a ride back to Earth. At launch, it weighed about 1,054 pounds. That's around 478 kilograms. A vehicle carrying people for years would weigh far more. And even this stripped-down sprint didn't make Jupiter feel close. 13 months covers every season. A baby born near launch could be taking early steps by the encounter. Birthdays, repairs, illnesses, and ordinary days would keep arriving aboard the spacecraft. Earth would keep moving too. Then comes the awkward part. After traveling for more than a year, New Horizons spent only a brief period near Jupiter before continuing outward. It could gather data as it passed, but it couldn't settle into a home around the planet. A human mission could copy that fast path only by accepting the same bargain. No stop, no base near Jupiter, no landing on one of its moons, no return trip. Add any of those goals, and the spacecraft must carry more equipment. It must also lose the enormous speed that helped it arrive so quickly. New Horizons proved that a robot can reach Jupiter quickly by spaceflight standards. It also showed how slippery the word reach becomes. Flying past a planet is one mission. Arriving safely, living there, and coming home is another. So what would the people inside such a spacecraft have to survive before Jupiter even came into view? Engineers can shorten that trip on paper. Give the spacecraft a much stronger engine, a huge supply of power, and enough fuel or propellant, and the calendar begins to shrink. Some studies bring a crew to Jupiter in well under a year. A few push toward trips measured in months. Those numbers aren't fantasies. They come from real calculations using known physics. But a calculation can begin with machinery that doesn't exist yet. It can also assume that an early prototype will someday become light, reliable, affordable, and safe enough to place beside a human crew. Nuclear thermal propulsion is one example. Instead of burning fuel in the usual way, a reactor heats hydrogen until the gas rushes through a nozzle. The engine could use its propellant more efficiently than today's chemical rockets. NASA and DARPA have worked on a demonstration called Draco, aimed at testing such an engine in space. That's serious engineering. It's still a long way from carrying people to Jupiter. Other proposals go further. Nuclear electric systems use a reactor to make electricity, then feed that power into efficient electric thrusters. These engines sip propellant, but they push gently. Think of moving a heavy cart with one finger. Keep pressing for months, and it can build remarkable speed, though it won't leap away from Earth like a chemical rocket. Then there are fusion studies. Fusion is the process that powers the sun, pressed into service as an engine. In principle, it could provide high speed without demanding mountains of chemical fuel. In practice, nobody has built a working fusion spacecraft engine. We're still trying to make fusion power on Earth practical and economical. More extreme papers consider antimatter, beamed sails, or giant lasers that supply energy from far away. The equations may work. The required factories, reactors, cooling systems, launch networks, and safety records do not yet exist. And that last part is easy to miss. A faster engine changes more than the travel time. It changes the spacecraft around it. A powerful reactor needs shielding and cooling. Hydrogen needs bulky tanks. Electric thrusters need enormous power systems. A laser-driven craft needs the laser installation before it can leave. Every shortcut arrives with quite a lot of luggage. So the shorter calendars in research papers tell us something valuable. Jupiter isn't physically beyond a human lifetime. Known physics allows faster routes, but those routes usually assume an entire future space industry, not one miraculous engine fitted to a modern crew capsule. If we granted ourselves that future machinery, what would the months inside the spacecraft actually demand from the people making the trip? A long voyage can look strangely ordinary from inside the ship. You wake, eat, exercise, clean, work, and sleep within the same few rooms, while Jupiter remains months away. Nothing has to explode for the mission to become dangerous. The ship simply has to keep working every day. So do the people inside it. On Earth, a dripping pipe is annoying. On a spacecraft, water hiding behind a panel can reach wiring, feed mold, or escape the system meant to recover it. A clogged filter raises carbon dioxide. A weak fan leaves warm pockets where equipment overheats. A loose fastener drifts away and waits for somebody to find it. Each problem is small. The crew still has to notice it, understand it, and fix it with whatever came aboard. That changes the job. Astronauts aren't just passengers enduring a long ride. They become plumbers, electricians, mechanics, medics, cleaners, cooks, and laboratory technicians. They also remain the only people available to help one another through months of confinement. Nobody gets to go home after a bad shift. The International Space Station gives us a close example. Crews spend a large share of their working time maintaining the place that keeps them alive. They replace pumps, inspect seals, clean vents, service toilets, and chase small faults through crowded racks. Spare parts arrive from Earth several times a year. A Jupiter ship would leave that supply chain behind. Then there's the human body. Without enough exercise, muscles shrink and bones lose minerals in microgravity. Fluids shift toward the head. Balance changes. Vision can change. NASA crews on the space station counter this with roughly 2 hours of exercise each day, using machines built to work without ordinary weights. That daily protection takes time, space, food, energy, and equipment that can also fail. Radiation adds another burden. Beyond Earth's magnetic field, the crew receives more exposure from high-energy particles in space. Shielding can reduce the dose, but it adds mass. A solar storm may force everyone into a better protected shelter for hours or days. The shelter still needs air, water, waste handling, and enough room for several tired people who would rather be anywhere else. Even meals become part of the machinery. Food must remain safe and tolerable for months. Water has to be recovered and cleaned again and again. Waste cannot simply pile up in a corner. Clothing, skin cells, crumbs, hair, microbes and smells all enter a closed environment. The ship ages because people live in it, and people stay healthy only by constantly caring for the ship. There's a social cost too. Privacy is scarce. Sleep can be disturbed by noise, schedules, or worry. A minor habit becomes impressive after the 400th repetition. Crews need enough structure to prevent boredom, but enough freedom to avoid feeling controlled every minute. They must handle conflict without letting it damage work that keeps everyone alive. None of these burdens alone makes the voyage impossible. The danger comes from accumulation. One sore shoulder, one failing valve, one poor night's sleep, one missing spare, then another and another, with no weekend and no repair crew on the way. So a fast engine may shorten the calendar, but the crew still has to carry a small world through every day on it. What keeps that world alive when its supplies, machines and people all depend on power that cannot stop? A spacecraft can reach Jupiter with every major system still working and still arrive worn down. The engines may be ready, the crew may be standing, the mission may look healthy on a checklist, but none of them has the reserve they had on departure day. Think of an old phone battery. At first, you leave home without checking it. Months later, you watch the percentage because 10% no longer means what it used to. The phone still works, you just plan around its weakness. A crew's reserve changes in a similar way. A small loss of muscle can make a heavy repair harder. A tooth that began aching during the cruise may now limit sleep. A medication supply may be lower than expected. One astronaut may have recovered from an infection but still tire faster. Each problem can be manageable by itself. Together, they narrow the crew's choices. The spacecraft loses room to maneuver as well. Filters gather debris. Pumps collect thousands of extra hours. Seals endure repeated heating and cooling. Electronics absorb radiation. Tools get used. Spare parts become replacement parts. A repair that once seemed affordable may now consume the last backup for another machine. And some losses cannot be packed away in a drawer. A scratched surface can be inspected, but not always restored. A crew member can exercise, but may not regain every bit of strength during the flight. Food, medicine, filters and cleaning supplies only move in one direction. The spacecraft arrives carrying an account of everything the cruise has already cost. A spent margin rarely looks like a dramatic failure. It's the slow loss of options. Suppose a cooling pump begins making an unfamiliar sound near Jupiter. Early in the trip, the crew might shut it down, open the housing, and replace several parts. At arrival, that same repair carries more risk. The astronaut doing it may have weaker grip strength. The spare bearing may be the only one left. A second pump may already be running slightly hot. Even the hours spent on the repair have a cost, because the crew has entered the busiest part of the mission. So they may keep the pump running and watch it closely. That protects the spare, but risks a larger failure. Or they may replace it immediately, using their last good bearing. That protects the cooling loop, but leaves no simple answer if another pump fails later. Neither choice is careless. Both are shaped by what the cruise has already taken. The same decision made 6 months earlier could have a different answer, because the crew had more strength, more time, and more working backups. This changes the meaning of arrival. Reaching Jupiter isn't like stepping across a finish line. It's like reaching the start of a difficult shift after you've already worked all night. The crew must begin orbit operations, navigation checks, science work, and constant maintenance with bodies and machines that have aged together. Mission planners can add supplies and duplicate equipment. They can schedule exercise, medical checks, and preventive repairs. But every extra spare adds mass. Every backup needs power, storage, and testing. Some backups need backups of their own. You can carry more reserve, but never an unlimited amount. That leaves a choice before the spacecraft ever launches. How much reserve must still remain when the crew reaches Jupiter, and what must they give up to carry it there? Sunlight near Earth feels so dependable that spacecraft can treat it almost like a wall outlet. Turn a panel toward the sun, and electrical power arrives. But on the way to Jupiter, that familiar light thins until noon becomes a much weaker kind of day. The sun still looks bright to human eyes. The difference shows up in every machine that depends on it. Jupiter orbits about 5 times farther from the sun than Earth does. Light spreads as it travels, like the glow from a lamp covering a wider wall. So the power available there isn't 1/5 of what Earth receives. It's closer to 1/25. Distance multiplies the problem faster than our everyday instincts expect. That changes the spacecraft before anyone builds it. Near Earth, a modest solar array can run computers, pumps, heaters, navigation equipment, and scientific instruments. Near Jupiter, the same array produces only a small share of that power. To make up the difference, engineers need much more collecting area. The wings grow longer, their supports grow heavier. Motors must unfold and aim the added structure. Wiring runs farther. Hinges become larger parts of the mission. Even keeping those broad panels steady can affect how the spacecraft points and moves. NASA's Juno spacecraft showed what that looks like. When it launched in 2011, it carried 3 long solar wings. Together, they held more than 18,000 solar cells. Near Earth, those cells could have produced around 14 kilowatts. At Jupiter, they supplied only about 500 watts. That's roughly enough for a few household appliances, while an entire spacecraft worked beside the largest planet in the solar system. A crewed ship would ask for far more. People need air moved and cleaned. Water must circulate. Cabins need heat. Food storage, lights, computers, medical equipment, and waste systems all draw power. Some loads can pause, breathing cannot. Neither can every heater when the sun has become a small, distant source of warmth. You could switch off a lamp and barely notice. But saving electricity only goes so far. A stopped cooling pump can ruin equipment. A heater left off may freeze a line that took years to send there. Power shortages become physical failures. Batteries help, but batteries don't create energy. They only hold energy gathered earlier. Making them larger adds mass, and that mass needs fuel to move. More batteries also need wiring, controls, temperature management, and protection from faults. Engineers can choose another source. Radioisotope generators turn heat from radioactive decay into electricity. Reactors could provide much more power for a future crewed mission. Both reduce dependence on sunlight, but they bring shielding, cooling, safety, testing, and political constraints. They also add equipment that must work for years without a repair shop nearby. So power isn't a box added after the ship is designed. It helps decide the ship's size, shape, cooling system, spare parts, and fuel. A larger power system can protect the crew, yet carrying it consumes some of the reserve meant to protect them. By the time Jupiter fills the windows, fading sunlight has already influenced almost every kilogram that arrived with the crew. And if power has become this scarce, what happens when they need to send information across the same enormous distance? Europa Clipper looks less like a compact robot and more like a small building that learned to fly. With its solar arrays spread wide, it stretches about 100 feet from end to end, roughly 30 meters. That span is longer than a basketball court is wide. Yet the main spacecraft body is only about 16 feet tall, or 5 meters. Most of what you see is wing, 2 enormous solar arrays, each divided into 5 panels and folded for launch. The size can seem excessive until you remember where Clipper is going. Near Jupiter, every square meter of solar panel receives much less sunlight than it would near Earth, so the spacecraft needs a great deal of collecting area just to run its instruments, heaters, computer, radio, and other basic equipment. Those broad wings aren't decoration. They're the physical price of getting electricity so far from the sun. NASA built Europa Clipper as its largest spacecraft made for a planetary mission. At launch, it weighed about 13,000 pounds, close to 6,000 kilograms. Nearly half of that mass was propellant, needed to steer the spacecraft during its long trip and its years around Jupiter. Then there is the radiation. Jupiter traps charged particles in a powerful magnetic field. Near Europa, those particles can damage electronics and gradually corrupt the systems a robot depends on. Clipper cannot step inside, close a door, and wait for the storm to pass. Its equipment must keep working through repeated encounters. Engineers answered by placing many sensitive electronics inside a thick-walled metal vault. It works a little like keeping valuables in a safe, except the threat is invisible radiation arriving from every direction. The vault reduces the dose, while carefully chosen components and backup systems add another layer of protection. That protection has weight. Weight needs structure. Structure needs fuel to move. Fuel needs a larger launch vehicle. Each answer pushes on several other parts of the spacecraft. The solar arrays create their own problems. They must survive launch while folded tightly against the body. Later, they must unfold in space and remain stable while the spacecraft points its instruments. They also need to work in the cold, after years of travel, with no technician nearby to free a stubborn hinge. Even the instruments have to share a crowded set of demands. Some need a clear view of Europa. Some need distance from electrical noise. The antenna must communicate with Earth. The radiators must release heat. The propulsion system must fire without spraying sensitive surfaces. A spacecraft this large is still a careful compromise over where every part can safely sit. And this is only a robot. It doesn't breathe, drink, eat, sleep, or need protection from months of weightlessness. It carries no living quarters, medical equipment, exercise machines, food stores, or human-scale escape system. Europa Clipper shows us the environmental bill before a single person comes aboard. Its long wings and armored electronics record the same fact in aluminium, wiring, and glass. Reaching Jupiter is only part of the job. The spacecraft must remain powered, warm, stable, and functional after it gets there. So if Jupiter already turns an uncrewed probe into a flying structure 100 feet across, how much more protection would a human body require? On Earth, asking for help feels almost instant. A crew near Jupiter could send a simple message home, then wait more than an hour for the reply. The delay changes as Earth and Jupiter move around the Sun. At their closest, they're about 365 million miles apart, roughly 588 million kilometers. At their farthest, that gap grows to about 601 million miles, or 968 million kilometers. Light crosses those distances faster than anything else can. Even so, a radio message needs about 33 to 54 minutes to travel one way. A reply takes the same time coming back, so the shortest possible exchange lasts more than an hour. Near the far end, it can take almost 2. That sounds like a communications detail until something breaks. A warning appears on a control panel. The crew sends the readings to Earth and asks what they mean. Nobody at Mission Control has heard the request yet. For the next half hour or more, the people aboard are entirely on their own. Engineers finally receive the data, study it, discuss the choices, and send instructions. Then those instructions spend another half hour crossing space. By the time the answer arrives, the original problem may have changed. A pump may have stopped. A battery may be draining. The crew may already have chosen a repair, because waiting was itself a decision. NASA lives with this delay every time it operates a spacecraft at Jupiter. When Juno receives commands through the Deep Space Network, the spacecraft cannot be flown like a drone over a nearby field. Engineers prepare sequences in advance. Juno then carries them out without anyone on Earth watching each move in real time. For a robot, that can be planned around. If a command goes wrong, the spacecraft may enter a protective state and wait. A human crew would face messier problems. People get injured, smoke spreads, machines fail in combinations that weren't included in the checklist. The crew would still talk with Earth. Doctors could review medical data. Engineers could work through unfamiliar faults. Families could exchange recorded messages. But none of those conversations would feel live. Even two people speaking casually would have to take turns across a gap longer than a television episode. You could ask a question, make lunch, and still be waiting for the first words of the answer. So distance changes more than the antenna and transmitter. It changes who must be allowed to decide. A Jupiter crew would need wider authority than astronauts near Earth. The ship would need software that can diagnose trouble locally. Procedures would have to assume that mission control is informed, capable, and unavailable at the exact moment it is needed. Every urgent choice would belong first to the people inside the spacecraft. Earth could advise them later. It could confirm that they chose well, or explain what they missed. But it could not reach into the moment and help them choose. And if help can no longer arrive in time, how much of Earth must the crew carry with them? A small mission control has to travel with the crew. Not the people in Houston, of course, but much of what those people know. Medical records, repair manuals, diagnostic software, spare parts, and enough training to use all of it when nobody on Earth can join the conversation in time. The strange part is that Earth might still hear about an emergency in great detail. Deep space antennas can receive weak signals across enormous distances. A spacecraft can send instrument readings, medical scans, photographs, and engineering logs. With enough power, careful aiming, and time, a great deal of information can make it home. That success can fool us. A downloaded heart scan proves that communication worked. It doesn't put a doctor beside the patient. A stream of engine data may tell engineers exactly which valve failed. Their reply can't arrive during those first few minutes when the crew must stop the damage. It's like sending a perfect recording of a house fire to the fire station, then waiting more than an hour for anyone there to answer. The recording could be clear. The firefighters could understand every detail. The house still needs someone inside who knows where the extinguisher is, how to use it, and when the room is no longer safe. Piloting has the same limit. Earth can plan a course, receive navigation data, and send later updates. It can inspect what happened after the danger has passed. But it can't steer through a sudden fault as if the spacecraft were a remote-controlled vehicle. By the time a warning reaches the ground, the ship has already moved on. By the time instructions return, the original problem may have changed completely. So the crew becomes its own clinic, repair shop, and flight control room. That means carrying more than equipment. The people need skills that overlap. A physician may have to repair a life support sensor. An engineer may need to assist with surgery. Everyone must understand enough of the ship to keep one person's illness from becoming everybody's emergency. Even familiar medical care becomes harder. On Earth, a doctor can call another doctor, order a new test, or send a patient to a better equipped hospital. Far from Earth, the available room, tools, medicine, and trained hands are all the crew has. There is no ambulance coming from the next town. If a treatment fails, they must find another answer from what is already aboard. The software would need to do more than display alarms. It could compare symptoms, test possible faults, and explain why it recommends a step. Yet the crew would still need to challenge it. A damaged sensor can report the wrong temperature. A medical model can misread an unusual patient. Blind trust would be dangerous. So would ignoring the machine whenever its advice feels inconvenient. None of this makes Earth irrelevant. Ground teams could study slow problems, compare months of data, and prepare procedures for risks that haven't become urgent yet. They could bring thousands of specialists into one long conversation. They might still be the largest support team the crew has ever had. They just wouldn't be present in the ordinary sense. That changes what a successful mission means. Returning data proves the connection survived. Keeping people alive proves the crew could act without waiting for it. Once the spacecraft becomes its own outpost, what hazards must that outpost survive before Earth's advice can arrive? Many radiation hazards occupy a limited region that a spacecraft can go around. Jupiter's is closer to a weather system that fills the entire map, with conditions changing as the spacecraft moves through it. The source begins deep inside Jupiter. Metallic hydrogen conducts electricity, while the planet turns once in just under 10 hours. Together, they produce the strongest planetary magnetic field in the solar system. That field catches charged particles and forces many of them to travel with the planet's rapid spin. You can think of a snow globe being turned again and again, except the flakes are electrons and ions moving fast enough to damage machines and living tissue. Jupiter keeps sweeping those particles around. Some gain energy as they go. The result is a set of radiation belts far more severe than the belts around Earth. But the belts are only part of the structure. The solar wind pushes against Jupiter's magnetic field on the side facing the Sun. Behind the planet, the field stretches away into a long magnetic tail. Its size changes with conditions in the solar wind, so there isn't one fixed border waiting to be crossed. On the sunward side, that border often stands several million miles from Jupiter. That's several million kilometers. In the other direction, the tail extends for hundreds of millions of miles, or hundreds of millions of kilometers. It can reach beyond Saturn's orbit. A magnetic system made by one planet can stretch across a large part of the outer solar system. Pioneer 10 first measured Jupiter's magnetic environment up close in 1973. Its instruments found radiation so intense that some readings exceeded expectations. Later, Galileo spent years moving through the system. Juno, arriving in 2016, followed a very different path. It swings close over Jupiter's poles, then retreats far away, limiting how long it remains in the worst regions. That route is part of the protection. At Jupiter, navigation isn't only about reaching a destination with the least fuel. A shorter path may carry a larger radiation dose. A slower path may expose the spacecraft to repeated passes through charged particle regions. Even the direction of approach can change which instruments remain usable and how much shielding the crew needs around them. Radiation also accumulates. One pass might weaken electronics without causing an obvious failure. Later passes add more damage. Detectors grow noisy. Memory can flip bits. Solar panels lose performance. Materials become brittle. For people, the dose reaches cells whether or not anyone feels it happening. So the crew can't treat Jupiter as a safe open space with one dangerous patch. The hazard shapes routes, schedules, spacecraft layout, maintenance, and the time anyone can spend away from the best shielded compartment. If the whole system is part of the storm, where could a crew ever find shelter within it? A route through Jupiter's neighborhood would look less like crossing an empty sea and more like walking across a flooded street. You don't aim straight at the door. You watch where the water runs fastest, find the shallow ground, and accept that the safer path may be longer. Jupiter's radiation belts force the same kind of choice. Charged particles crowd into broad regions around the planet. Some areas carry far more of them than others. The strength can change with distance, latitude, and the shape of the magnetic field, so a flight path on a map is also a path through different radiation doses. That changes what fastest route means. The shortest line may carry the spacecraft through a harsh belt for too long. A wider curve may take more fuel and more days, yet spare the electronics a large part of their total exposure. Mission planners have to trade time, propellant, instrument health, and radiation dose against one another. They can also change the angle of approach. A spacecraft entering near Jupiter's magnetic equator may meet a different particle environment from one arriving at a steeper angle. Timing counts too. The belts aren't painted rings with fixed edges. They respond to Jupiter's magnetic field and to material moving through the system. Engineers plan with models, then update those models when the spacecraft begins measuring the real conditions. This is why shielding alone can't solve the problem. Adding metal makes a spacecraft heavier. More weight demands more fuel, a larger rocket, or fewer scientific instruments. And when very energetic particles strike thick shielding, they can produce secondary radiation inside it. The protective wall can become part of the physics you're trying to manage. Routing reduces the amount of radiation that shielding must handle. It lets the spacecraft spend less time in the worst regions and cross them when necessary. Instruments may be turned off during a rough passage. Sensitive electronics can sit inside a protected vault. Some observations may happen quickly, with data stored until the spacecraft reaches a calmer area. NASA's Juno spacecraft was built around this strategy. Rather than circling Jupiter along its equator, Juno follows a long polar orbit. It sweeps close over the cloud tops, then travels far away before returning. Each close pass is brief. The path avoids spending the entire mission inside the strongest part of the belts. Even so, the route isn't a magic tunnel. Juno still receives radiation. Its electronics sit behind thick titanium walls, and each orbit adds to the mission's total dose. The safer path lowers the damage. It doesn't make Jupiter safe. That is the shift. Radiation near Jupiter isn't merely bad weather that a sturdy spacecraft pushes through. It redraws the roads, and once every road carries some dose, how do you choose a place to stop? A safe route near Jupiter looks rather strange on paper. Juno doesn't stay close to the planet after collecting its measurements. It leaves again, climbing millions of miles away before gravity brings it back for another fast pass. That long loop is deliberate. Juno spends most of each orbit far from the worst radiation. Then, near Jupiter, the spacecraft moves quickly through the dangerous region. Its closest approach lasts hours, not weeks. The science team gets a short working window, followed by a long retreat. It's a little like repairing equipment beside a hot furnace. You don't build your desk next to the open door. You step in, do the job, and step back before the heat causes too much harm. Juno uses speed and distance in much the same way. The spacecraft entered orbit around Jupiter on July 4, 2016. Since then, each close approach has followed a carefully timed sequence. Instruments turn toward the planet. Juno measures gravity, magnetic fields, particles, and microwave radiation from deep below the clouds. Then the pass ends, and the spacecraft heads outward again. That repeated escape is part of the mission design. Success doesn't mean remaining unharmed in one comfortable orbit. It means accepting a limited dose, leaving the dangerous area, and returning only when the next pass is worth the added damage. Time near Jupiter becomes something the mission must spend carefully. Even Juno's instruments reveal how seriously the team treats that bargain. A radiation monitor tracks energetic particles around the spacecraft. Engineers compare those readings with predictions and watch how the hardware changes over time. Some instruments have lost capability, others have needed new operating plans as the dose accumulated. Survival, here, includes knowing when to change the plan. Juno has also survived longer than its original prime mission required. That doesn't show that Jupiter's radiation was exaggerated. It shows that the protections and flight path worked well enough to preserve useful spacecraft life. Avoidance produced endurance. And the orbit has another advantage. Passing over the poles lets Juno sample regions that earlier spacecraft could not study in the same way. The route chosen for survival also opened a new view of Jupiter's atmosphere and magnetic environment. The constraint shaped the science. But there's no free passage. Every close approach spends part of the spacecraft's remaining tolerance. Engineers can shield electronics, shorten exposures, and change how instruments operate. They cannot reset the radiation dose to zero. Each return is therefore both a scientific opportunity and a small withdrawal from a limited account. So Juno survives Jupiter by moving with care. It approaches, works quickly, and withdraws. That looping path is flown evidence that near Jupiter, where you travel, can matter as much as what your spacecraft is made from. A visitor can keep passing through. But what happens when the mission needs to remain in one place? Europa makes staying seem worth almost any trouble. Its surface is a shell of water ice, crossed by long brown cracks and ridges. Beneath that shell, the evidence points to a global ocean. It may hold more liquid water than all of Earth's oceans combined. That alone would pull our attention. But Europa adds something more. Its ocean may touch a rocky seafloor. If water and warm rock meet there, chemical reactions could provide energy. On Earth, Similar chemistry supports living communities around deep-sea vents, far beyond sunlight. No one knows whether Europa has vents. No one knows whether its ocean contains life. We haven't sampled that hidden water, and we haven't seen the seafloor. The case rests on measurements gathered from above. Europa's magnetic response, its young-looking surface, its fractured ice, and the way its interior flexes under Jupiter's gravity. In the late 1990s, NASA's Galileo spacecraft made repeated passes by Europa. Its instruments found signs that fit a salty, electrically conducting layer beneath the ice. Then, in 2012, the Hubble Space Telescope recorded possible water vapor above Europa's southern region. Later observations didn't always find it again. The suspected plumes may be brief, faint, or something else entirely. That uncertainty doesn't weaken Europa's pull. It sharpens it. A plume, if one can be confirmed and crossed, might carry material from below without requiring a drill through miles of ice. A lander could inspect surface material that may have risen from the ocean. An orbiter could map the shell and search for places where the interior has left recent traces. And this is where people enter the story. Robots are excellent at enduring distance, following careful instructions and waiting through long communication delays. Humans can notice odd details, change plans quickly, repair equipment, and choose the next sample while standing beside the last one. On a world with broken terrain and uncertain clues, that flexibility feels deeply appealing. That possibility is difficult to leave to machines alone. You can see the emotional case. If Europa's ocean offers even a small chance of answering whether life began twice in one solar system, sending people closer can seem like courage meeting its proper destination. But scientific importance doesn't make a place suitable for human work. The same closeness to Jupiter that needs Europa's interior also fills its surroundings with charged particles. Europa invites us with water, chemistry, and one of biology's oldest questions. So what would that invitation demand from a human body that had to stay? A human mission usually sounds like a job with a calendar. You travel, arrive, work through a list, and come home. On Europa, the calendar stops being the natural way to measure the danger. The more useful clock may be the one inside your cells. Jupiter surrounds itself with powerful radiation belts. They're filled with electrons, protons, and heavier charged particles racing through space. Europa orbits deep inside that storm. Its surface has no thick atmosphere to absorb the particles before they arrive, and almost no magnetic shield of its own to turn them aside. You can think of your skin as the cover of a very complicated instruction book. Ordinary sunlight can damage a few letters near the cover. Europa's radiation reaches farther, striking molecules throughout the body and breaking chemical bonds along the way. Some cells repair the damage, some die, others survive with mistakes written into their DNA. That doesn't mean a visitor would feel each particle hit. Radiation can be dangerously polite. There may be no burning air, no obvious beam, and no warning from your senses. Your equipment has to tell you what your body cannot. The dose would build while you worked. It would keep building as you walked, drilled, lifted samples, or waited beside a stubborn machine. A small delay wouldn't merely annoy the crew. It could consume part of the exposure limit planned for the entire visit. That changes the meaning of an ordinary problem. A jammed tool on Earth costs time. A jammed tool on Europa costs time and tissue. A torn glove, a slow airlock, or a rover that won't restart becomes more than an engineering nuisance. Every extra minute adds to damage that shielding and medicine can only reduce, not erase. This is why normal mission language starts to sound strange there. We talk about expeditions lasting weeks or months because people need time to do serious field work. Europa pushes in the other direction. Depending on shielding and location, dangerous exposure could arrive on the scale of hours or days, not careers, not even a comfortable research season. And the body doesn't reset when the lander door closes. Radiation injury can appear later as sickness, damaged bone marrow, cataracts, or a higher risk of cancer. The person who walks away from the surface still carries the record of being there. So a crew couldn't simply land, work carefully, and accept the usual hazards of exploration. They would need mass between themselves and Jupiter's particles almost every moment. But every kilogram sent that far is costly, and shielding has limits. If Europa gives people so little safe time above ground, where could they possibly live and work? A robot can tolerate Europa better than a person, but even the robot cannot arrive with its electronics exposed. Europa Clipper carries its most sensitive computers inside a protective metal vault. It's a little like putting the mission's nervous system inside a heavy safe. The vault is made from aluminium alloy. Its walls slow the charged particles that Jupiter sends through the spacecraft. Without that barrier, radiation would gradually damage the electronic parts inside. A computer may begin returning bad data, memory can become corrupted, a small component can fail, and there is no repair shop anywhere nearby. This is one reason Europa Clipper won't settle into orbit around Europa itself. Instead, it will orbit Jupiter and make repeated close passes by the Moon. Each flyby gives its instruments time to study the ice, gravity, magnetic environment, and thin atmosphere. Then the spacecraft moves farther away again, reducing its time in the worst radiation. You might expect a machine built to cross hundreds of millions of miles to stay once it arrives. Clipper cannot. The spacecraft has no skin to burn and no bone marrow to injure, yet its designers still had to ration its exposure. They chose parts that can survive radiation, added shielding and backup systems, then planned an orbit that carries the machine away after each close encounter. NASA engineers also placed many electronic components together inside the same vault. One shield can protect several systems at once, saving mass compared with wrapping every component separately. That matters when every extra pound must be launched from Earth and carried all the way to Jupiter. Even then, the protection isn't perfect. Some instruments must remain outside because they need a clear view or direct contact with the space around them. Those parts are chosen and built for the radiation they're expected to receive. Engineers can reduce the risk. They cannot make the radiation disappear. So Europa Clipper doesn't prove that working near Europa is easy. It shows why a machine is the right visitor. We can harden a robot, give it backup circuits, and send it through the dangerous region in short, planned passes. It needs no food, sleep, warmth, or medical care after coming home. If radiation eventually shortens the spacecraft's life, the loss will be painful and expensive. But it won't be a human death. The vault, the orbit, and the strict limits all tell us the same thing. Near Europa, survival begins by removing the human body from the job. But if people cannot remain on the surface, and even a robot must keep moving, could Europa itself provide the shielding a crew would need? Ganymede offers something Europa cannot. A compass placed near this moon would respond to a magnetic field generated inside the moon itself. No other moon in the solar system is known to make one. Earth does something similar. Motion in our planet's liquid metal core creates a magnetic field around us. That field pushes many charged particles away before they reach the atmosphere. Ganymede's field is much weaker, but the basic effect is real. It forms a small magnetic bubble around the moon. NASA's Galileo spacecraft detected this field during close passes in 1996. The measurements showed that Ganymede had its own magnetosphere, nested inside Jupiter's much larger one. It's a shield inside a shield, except the outer shield is also carrying the danger. Jupiter's magnetic field traps charged particles and drives them around the planet at high speed. Ganymede can redirect some of that flow. Near parts of the moon, particle levels fall. A crew or surface base might receive less radiation there than it would near Europa. That's a genuine advantage. It could reduce the mass of shielding a habitat needs. It could also give electronics a longer working life. For people trying to live anywhere in Jupiter's system, even a partial reduction could shape the whole design. Every kilogram of shielding saved is a kilogram a rocket doesn't have to push across space. But Ganymede's magnetic bubble is small, uneven, and surrounded by Jupiter's radiation environment. Some particles still enter it. Others travel along magnetic field lines toward the moon's polar regions. A magnetic field doesn't behave like a steel roof. It bends the paths of charged particles, and some paths still end at the surface. The surface offers another layer of protection. Ganymede is made from rock and ice, and a habitat buried beneath enough ice would block far more radiation than the magnetic field alone. You can treat the field as the first door, and the ice as the heavy wall behind it. Neither makes the location harmless. Together, they may make a protected base more practical. There is also distance. Ganymede orbits farther from Jupiter than Europa does, so it sits in a less punishing part of the radiation belts. Jupiter isn't surrounded by one flat wall of danger. Conditions change with distance, latitude, local magnetic fields and time. A place that's dangerous on one route may be less severe on another. So Ganymede is a fair exception to the bleakest view of the Jovian system. It has a weaker radiation environment than Europa, a natural magnetic field, and plenty of material that could become shielding. Those are serious assets. They're also partial ones. A crew still has to cross interplanetary space, slow down near Jupiter, and travel through its magnetic environment. The spacecraft needs shielding before anyone reaches the safer pocket. Solar storms remain a threat during the journey, so do long exposure to weightlessness, equipment failures, and the awkward business of carrying years of food, water, spare parts, and medicine. Ganymede improves the place where people might arrive. It doesn't simplify the voyage that gets them there. If even the best local shield leaves the larger mission intact, where in Jupiter's system does distance finally begin to help? A safer bedroom doesn't make an old house cheap to own. The roof still leaks, the wiring still needs replacing, and every box has to be carried up the same narrow stairs. Ganymede works much the same way. Its local advantages are real, but people can't use them without first building a much larger system around them. Start with the route. Jupiter is not a single destination with 4 convenient moons parked beside it. Each moon moves around the planet at its own speed. A spacecraft arriving from Earth must meet that moving target, while Jupiter's gravity pulls hard on everything nearby. Miss the timing, and the ship may need extra fuel, another orbit, or a long wait before the geometry lines up again. There is no roadside stop where a crew can simply pull over and reconsider. Fuel shapes nearly every other decision. More shielding means more mass. More mass takes more fuel to accelerate and slow down. Extra fuel adds still more mass, which can demand an even larger launch vehicle. Engineers call this the rocket equation, but you already know its basic cruelty from carrying groceries. Add one heavy bag, and the trip gets harder. Add a bag containing supplies for carrying the first bag, and the problem begins feeding itself. Robotic missions have learned to bargain with this problem. Galileo reached Jupiter in 1995, after using the gravity of Venus and Earth to gain speed. Juno arrived in 2016, after an Earth flyby of its own. These routes saved propellant, but they also added years and placed strict limits on when the spacecraft could leave. A crewed mission could use similar tricks, but every added year would require more food, more maintenance, and more chances for something small to become serious. Robots can wait through a slow route without getting hungry. People are less accommodating. Arrival creates another bill. A spacecraft falling toward Jupiter gains enormous speed. It must lose enough of that speed to avoid flying past, plunging too close, or entering the wrong orbit. Chemical engines can break quickly, but they consume large amounts of propellant. Electric engines use propellant slowly and efficiently, but their gentle push takes time. A human ship may need both, strong engines for moments that can't wait, and efficient engines for the long work between them. Then the mission needs places to hide, repair, and wait. Cargo might be sent ahead. Fuel could be stored in orbit. Uncrewed vehicles could inspect landing sites and test equipment before people leave Earth. That sounds sensible, because it is. It also turns one voyage into a chain of launches, transfers, dockings, and machines that must work after years in deep space. Each link depends on the others. A failed cargo flight might delay the crew. A failed fuel depot could cancel the departure home. This is the larger cost surrounding Ganymede. The safer room may lower the shielding needed after arrival, and it may give a crew a better place to work. but the house still includes every launch, every engine burn, every supply cache, and every piece of hardware waiting far beyond immediate rescue. So if distance from Jupiter can lower one danger, how far out must a crew go before the whole mission begins to get easier? Callisto circles far beyond the bright bands and violent weather near Jupiter. That extra distance makes it the least dangerous of the 4 large Jovian moons for a human crew. Its advantage is simple. Jupiter's magnetic field traps charged particles and drives them around the planet at high speed. Near the inner moons, those particles create radiation levels that can damage electronics and harm people. Callisto sits outside the worst of those belts. Radiation still reaches it, but the dose is far lower than it is on Europa, and lower than on Ganymede. You can think of it as standing farther from a fire. The room hasn't become cold. You've only moved away from the fiercest heat. At Callisto, a habitat would still need shielding, crews would still track their exposure, shelter during solar storms, and limit time outside, but radiation would no longer dominate every hour in quite the same way. That changes what engineers can reasonably leave there. Communications gear, fuel tanks, power systems, and surface vehicles would face less punishment from charged particles. Machines could still fail from cold, dust, age, or ordinary bad luck. Jupiter simply becomes less eager to ruin them through radiation. Callisto is also large enough to offer real ground beneath a lander. Its surface is mostly ice and rock, battered by ancient impacts. There may be usable water in that ice, although extracting it would take heavy equipment and a great deal of power. Gravity is weak, about 1/8 of Earth's. That helps with launches, but it also raises long-term concerns for human health. Then there is the distance that buys all this relief. Callisto travels about 1,880,000 kilometers from Jupiter, or roughly 1,170,000 miles. A spacecraft based there would be well placed to watch the Jovian system without living inside its harshest region. But every trip toward Europa, Ganymede, or Jupiter itself would require time, fuel, and another passage into stronger radiation. So Callisto offers a rather unheroic kind of success. You arrive at Jupiter by refusing to get very close to Jupiter. The safest major moon is useful because it stands back, giving people and machines a place where survival may depend less on massive shielding and constant retreat. That doesn't make Callisto comfortable. It is remote, frozen, airless, and almost unimaginably far from help. It only changes the balance. Instead of choosing the most exciting destination and fighting its dangers every day, a crew could begin from the place that asks the least of fragile human bodies. But what would people actually build there? And how would a distant moon become a working base rather than another expensive place to survive? A serious mission study often begins with a rather uncomfortable spreadsheet. Every kilogram must be launched, accelerated, slowed down, powered, heated, and protected. Add people, and the columns become much less forgiving. They need food, water, living space, medical supplies, and a way home. Jupiter then adds years of travel and a radiation environment that can punish the wrong destination. This is why Callisto appears in studies that were never written by science fiction fans. Engineers start with different engines, power systems, and mission dates. They test ambitious routes. Then the architecture backs away from Jupiter and settles near its outermost large moon. One well-known example came from NASA's Human Outer Planets Exploration Study, usually shortened to HOPE. The team examined how people might work in the Jupiter system using advanced propulsion and nuclear power. Europa was the scientific prize. Its hidden ocean made it irresistible, but placing a crew close to Europa meant placing them deep inside Jupiter's radiation belts. So the study separated human presence from the most dangerous work. Astronauts could operate from Callisto while robotic machines traveled inward. The people would still be close enough to guide complex exploration without waiting through the long communication delay from Earth. It was less like camping beside the excavation and more like running heavy equipment from a protected control room across town. Callisto also offered local material. Its surface contains abundant water ice. A future base might turn that ice into drinking water, breathable oxygen, and perhaps rocket propellant. None of this would be easy. Mining frozen ground in extreme cold is difficult even before every broken seal becomes a serious problem. Still, carrying machinery is better than carrying every glass of water and every tank of fuel from Earth. Other architecture work has changed the assumed vehicles and power sources. Some concepts lean on nuclear electric propulsion. Others give more work to robots or place infrastructure in orbit instead of on the ground. The hardware moves around, but the compromise often survives. Do the dangerous science farther inward. Keep the crew, supplies, and repair shop near Callisto. That repeated result tells us something important. Callisto isn't compelling because one perfect mission plan selected it. It remains useful after the plan changes. Better engines shorten parts of the trip, but they don't remove Jupiter's radiation. Smarter robots reduce the crew's workload, but they make a nearby human control point more valuable. More capable power systems help a base survive, yet they don't make Europa gentle. Different assumptions keep producing the same retreat. Callisto becomes the place where human limits and scientific ambition can share an address. But a design study can move flawless symbols across a page. What happens when real spacecraft finally enter the Jupiter system and measure the route for themselves? JUICE will arrive at Jupiter in 2031, carrying 10 scientific instruments and a problem every mission planner there must respect. The spacecraft can visit several icy moons, but it cannot treat every close pass as equally affordable. Around Jupiter, location changes the radiation dose. Europa sits deep inside Jupiter's harsh radiation belts. It is one of the most tempting places to study because an ocean probably lies beneath its ice. Yet JUICE is scheduled to fly past Europa only twice, 2 brief encounters. The spacecraft will gather its measurements, then move on. Callisto gets a very different schedule. JUICE is planned to make 21 flybys of Callisto before settling into orbit around Ganymede. 21 passes by the outer moon, compared with 2 near Europa. That difference isn't an accident, and it doesn't mean Callisto is 21 times more interesting. It means time near each moon carries a different cost. You can think of the spacecraft as having a radiation allowance. Every trip through the stronger belts spends part of that allowance. Electronics can fail gradually as energetic particles damage components and upset stored information. Instruments can collect noise along with data. Solar panels lose performance. The spacecraft has protection, backup systems, and carefully chosen parts, but none of those makes the dose disappear. So mission planners budget exposure the way a diver budgets air. A fascinating cave may deserve a visit, but you don't stay there simply because there is more to see. You collect what you can, then return to a place where the danger builds more slowly. Callisto offers that place. Its orbit lies beyond the strongest part of Jupiter's radiation environment. JUICE can pass it again and again while changing its path through the system. Those flybys also use Callisto's gravity to reshape the spacecraft's orbit without demanding all that work from its engines. The moon becomes both a scientific target and part of the route itself. There's a small practical comedy in this. Europe's most ambitious mission to Jupiter's icy moons must ration its meetings with Europa. The moon, with the famous hidden ocean, gets 2 short appointments. Callisto, often treated as the less glamorous neighbor, keeps appearing on the calendar. JUICE won't use Callisto as a human base, of course. It is a robotic spacecraft, and its final orbital destination is Ganymede. But its itinerary reveals the same pressure seen in crude mission studies. When planners balance scientific reward against radiation, the outer moon becomes easier to use repeatedly. Callisto's appeal survives contact with actual navigation, actual hardware, and a finite mission lifetime. That makes it more than somewhere worth studying. It is the part of the Jovian system that missions can keep returning to without paying Europa's price each time. If robots already ration their exposure this carefully, what would it take to protect people who had to remain there for months or years? Juno carries its most sensitive electronics inside a metal box about the size of a large household oven. The box is so plain that beside the spacecraft's wide solar panels and long instruments, it barely looks like the part keeping the mission alive. Engineers call it the radiation vault. Its walls are made from titanium about 4/10 of an inch thick, or 1 centimeter. The vault weighs nearly 440 pounds, around 200 kilograms. That is a lot of spacecraft mass devoted to something that neither takes measurements nor sends signals home. Its job is simply to stand in the way. Radiation shielding works a little like sheltering behind a brick wall during a hailstorm. The wall doesn't stop the storm outside. It gives the hail more material to strike before it reaches you. Inside Juno's vault, energetic particles must cross titanium before reaching the computers, power controls, and other electronics. Some particles collide with atoms in the metal and lose energy. Others change direction. The vault cannot catch everything, and impacts can produce secondary radiation. Still, it cuts the dose to the electronics by about 800 times compared with leaving them exposed. The storm remains outside, but the equipment inside receives a much smaller share of it. That reduction is what makes Juno's close passes possible. Since reaching Jupiter in 2016, the spacecraft has swept low over the planet's cloud tops again and again. Each orbit carries it through a radiation environment that can damage circuits, scramble stored information, and slowly weaken electronic parts. The hardware inside was chosen for radiation resistance too. Engineers also spread important functions across separate systems. If one part misbehaves, another may keep the spacecraft working. The vault is one layer in that defense, not a magic box. And it has worked. Juno has remained productive far beyond its original prime mission, while repeated passes have added to the radiation dose stored in its materials. A particle that causes no immediate failure can still leave a tiny scar. Enough scars eventually change how a component behaves. So shielding is real engineering. We have sent a machine into Jupiter's radiation belts with a purpose-built armored room, and that room has protected its working parts for years. The cost is visible in every pound of titanium that could have been fuel, an instrument, or another piece of equipment. Even a small protected box asks the spacecraft to carry a heavy answer. For a spacecraft computer, that trade can be calculated with remarkable precision. Engineers know the size of the box, the parts inside it, and roughly how much radiation the mission will deliver. But what happens when the protected thing is warm, living, and cannot be switched off? A person cannot live inside a metal vault built for a computer. The computer needs wires, cooling, and enough space to avoid touching the walls. A crew needs all of that, plus air, water, food, sleep, movement, medicine, and somewhere to put the waste. That changes the scale of the problem. A robotic vault protects a small set of parts. If one part fails, another may take over. The vault itself can be packed tightly because nobody has to climb inside and spend months there. Human beings need room to stand, work, exercise, wash, eat, and get away from one another occasionally. That last item may sound less scientific, but put several tired people in a cupboard for a year, and it becomes engineering very quickly. The protected space also has to contain the systems that keep them alive. Oxygen must be supplied or recovered. Carbon dioxide must be removed. Water must be stored and recycled. Heat must leave the cabin at a controlled rate. Food, medical supplies, tools, spare parts, and emergency equipment all need protected places too. You can shield the crew and leave the oxygen system outside, but that only moves the weak point. A damaged pump or control unit can make an intact cabin unlivable, so the protected region grows. Then its larger walls need more shielding. More shielding adds mass, and that mass needs structural support. The support takes up room and adds still more mass. It works a little like packing for a long winter in a remote house. Protecting one person means more than giving them a thick coat. The pipes cannot freeze. The food has to last. The heater needs fuel. And if the heater breaks, there must be another way to stay warm. Survival belongs to the whole arrangement, not one well-covered body. Space crews need the same kind of backup. A single air scrubber is not enough. Neither is one cooling loop or one water pump. Some equipment must be duplicated. Other equipment needs spare parts and a way to reach it for repairs. Those backups also sit inside the protection, using volume and adding weight. This is why human habitat is not simply a robotic vault made larger. It is a livable ecology wrapped in armor. People and machines keep one another alive inside it, every hour, with no pause button and no quick delivery from home. Engineers can reduce the burden by arranging supplies around occupied areas. Water, food, and even waste can absorb some radiation while serving another purpose. But every wall, tank, passage, and backup still has to fit into one connected shelter. So, once the protected box has become a protected world, how do you move all of it where it needs to go? A ship feels its weight long before it reaches deep space. First, every shield panel, water tank, and protected room must rise from Earth. Gravity charges for every extra pound. A heavier ship needs a larger rocket, or several launches followed by assembly in orbit. Either choice adds hardware. Larger fuel tanks need stronger supports. Docking separate pieces needs engines, controls, and connections that cannot leak or jam. Protection makes the ship heavier, and lifting that protection adds another layer of weight around it. The same problem follows the crew after launch. A heavy ship is harder to speed up. It is also harder to turn and harder to slow down. You can feel the difference with two shopping carts. The empty one moves with a light shove. Fill the other with bags of concrete, and every change takes more effort. The cart does not care whether that weight is armor, food, or fuel. Spacecraft obey the same rule. More mass means the engines must push harder to produce the same change in motion. That requires more propellant. But propellant has mass too, so the ship needs propellant to move its shielding, then more propellant to move that first load of propellant. Tanks, pipes, pumps, and engine parts add their own share. This is the central trap. Shielding can work exactly as intended and still make the mission much harder. Success does not end the engineering problem. It spreads the problem into launch, steering, power, and braking. Nothing escapes the accounting, even when it protects life. Power systems feel it too. A larger habitat takes more electricity to heat, cool, monitor, and operate. It may need longer cables, more pumps, and more fans. Solar panels and their supports add mass. Another kind of power source still needs structure, controls, and cooling equipment. Every answer leaves the engines carrying something else. Then comes braking. A ship heading toward another world cannot stop using its engines and simply coast into place. It must lose speed with careful timing. A heavier ship needs more force, more time, more propellant, or some combination of all three. Get the arrival speed wrong, and the crew may pass the destination or enter the wrong orbit. Engineers can make parts serve two jobs. Water can shield the crew while remaining drinking water. Food can line a shelter before anyone eats it. Fuel and equipment can sit where they block some incoming particles. We can make each pound do more, but we cannot make the pound disappear. So the ship faces an awkward bargain. Thin protection risks the people inside. Thick protection burdens every engine burn from departure to arrival. If ordinary rockets make that bargain too costly, what kind of propulsion could move a well-protected human ship across the solar system? The strongest answer NASA studied was a ship that would use fusion, the same basic process that powers the Sun. In the HOPE study, short for Human Outer Planets Exploration, engineers treated fusion as a serious design case for carrying people to Jupiter's moon Callisto. This wasn't a claim that such an engine was ready. It was a way to ask what would change if it became ready. The study assumed a fusion system could release far more energy from each pound of fuel than chemical rockets can. That would let a heavy ship gain speed without devoting most of its mass to propellant. The proposed engine would fire small fusion targets again and again. Each burst would create hot plasma. Magnetic fields would direct that plasma backward, pushing the ship forward. It's less like one long explosion and more like a rapid series of tiny, controlled kicks. On paper, the payoff was enormous. The HOPE team examined a round trip to Callisto lasting roughly 5 years. That included travel in both directions and time near Jupiter. A mission using more familiar propulsion could keep a crew away much longer, or make the same payload too hard to move at all. Calendar relief changes almost everything. Fewer years in space mean less food, fewer replacement parts, and less time for equipment to fail. The crew receives a smaller lifetime dose of galactic cosmic rays. They also spend less of their lives inside a machine millions of miles from immediate help. And the ship can carry substantial protection without becoming completely immovable. Fusion doesn't erase the mass bargain. It gives engineers more room to negotiate with it. Still, the hopeful result rests on a very large condition. No fusion rocket has carried a crew, flown in space, or completed the repeated burns that a Callisto mission would require. Even fusion power on Earth remains an experimental field. A spacecraft version would also need radiators, magnets, power equipment, and a way to survive countless fusion pulses without wearing itself apart. Jupiter adds another limit. Callisto was chosen partly because it lies beyond the worst of the planet's radiation belts. Even so, the crew would arrive in a region where charged particles, navigation delays, and distance from Earth make every repair harder. So the HOPE case deserves to be taken seriously. It shows that much faster human travel to the outer solar system doesn't break known physics. It also shows the gap between a possible engine and an engine you would trust with several lives. If fusion can shorten the calendar but cannot yet leave the ground, is there any nearer-term system that offers part of the same relief? A 6-month trip to Jupiter sounds less like a mission and more like a promise. That promise has appeared around a proposed device called the Q thruster. The idea is unusually bold. A Q thruster would use electricity to produce thrust without carrying ordinary propellant. No tank of xenon, no stream of hot gas. The craft would push against quantum fields that are said to exist even in empty space. If that worked, the advantage would build slowly. The thrust might be tiny, but it could continue for months. A gentle push held long enough can produce a large change in speed. It's like leaning on a heavy shopping cart. Nothing dramatic happens at first. Keep pushing, and the cart eventually moves fast enough to become a problem. Some mission studies have used claimed Q thruster performance to sketch a Jupiter trip of roughly 6 months. That would cut years of waiting from many familiar flight plans. The spacecraft could accelerate through part of the trip, turn around, then slow down before arrival. But the claim comes with a very large asterisk. No Q thruster has shown reliable, independently confirmed thrust from the proposed quantum effect. Tiny forces are difficult to measure. Warm equipment can move air, cables can tug, magnetic fields can press against nearby hardware, even heat leaving a device unevenly can create a small recoil. When the expected thrust is extremely weak, those ordinary effects can look suspiciously like an engine. There is also the electricity bill. Continuous thrust needs continuous power. For a crewed craft with serious mass, the required power could reach far beyond what today's spacecraft can supply. Solar panels become less helpful as you travel away from the Sun. Near Jupiter, sunlight is only a small fraction of what reaches Earth. That leaves some form of compact nuclear power as the likely source. Yet the reactor, shielding, radiators, and electrical equipment all add mass. More mass demands more thrust. More thrust demands more power. The attractive little engine soon acquires a very large support system. So 6 months belongs in the category of calculated possibility, not demonstrated transport. The arithmetic may produce a short calendar. The hardware has not earned that calendar yet. Still, the exercise shows something valuable. Travel time isn't fixed by Jupiter's distance alone. It depends on how long an engine can keep changing the spacecraft's speed. A weak engine that runs steadily can sometimes beat a powerful engine that burns for minutes. On paper then, Jupiter can move much closer in time. It still doesn't become an ordinary place to reach. And if the engine depends on an effect we haven't proved, what kind of propulsion could offer steady thrust without asking physics for such a generous favor? A faster engine seems to remove the main objection to a human trip to Jupiter. Cut the cruise from years to months, and the mission begins to sound less like exile and more like a very long voyage. But the studies that grant us those faster engines tend to keep making the same choice. Their crews still head for Callisto. That repetition tells us more than the optimistic travel times do. Different engines can change the route from Earth. They can shorten the months spent between planets. Yet when the spacecraft reaches Jupiter, the destination map remains stubbornly familiar. Callisto sits far from Jupiter compared with the other large moons. That distance gives a crew a much gentler radiation environment than it would find near Europa or Io. Jupiter's magnetic field traps charged particles and drives them around the planet. Deeper inside that system, those particles become a serious problem for people and electronics. A quick cruise doesn't switch that field off. It's a little like reaching a dangerous coastline in a much faster ship. The improved engine gets you across the ocean sooner. It doesn't make every harbor equally safe. Once you arrive, reefs, storms, and shallow water still decide where you can anchor. Jupiter has its own version of that local hierarchy. Callisto is the forgiving outer stop. Ganymede lies deeper in. Europa is deeper still, inside a harsher radiation zone. Io is an extraordinary place to study, but an especially punishing place for a crew to remain. Advanced propulsion can help with some of this. More available thrust may allow quicker transfers between moons. A mission could spend less time crossing exposed regions. It might also carry more shielding, spare equipment or supplies, depending on the engine and spacecraft design. Those are real gains. They don't erase the ordering. This is why Callisto keeps surviving when mission designers change the propulsion assumptions. The engine may be nuclear. It may use electric thrust. It may belong to a more ambitious future study. Again and again, Callisto remains the sensible place to base people while machines travel farther inward. That destination choice is evidence. It shows which part of the problem the new engine has solved, and which part it has merely delivered us to more quickly. The long cruise may shrink. Jupiter's radiation, immense gravity, and difficult moon-to-moon travel are waiting at the other end. So the objection to human missions isn't simply that our engines are too slow. Even a generous propulsion case leaves us with a system where the most interesting destinations may not be the safest places to live. We can arrive sooner and still need to keep our distance. If Callisto is where people wait, then how do we explore the far more tempting world deeper inside Jupiter's radiation belt? Never is a dangerous word in science. It sounds like nature has posted a sign and locked the door. But nothing we've covered gives us that kind of certainty. No physical law says a person can never travel near Jupiter. No equation draws a permanent line beyond Mars and tells us to stay home. The limit is more practical than that. Human bodies may stop leading the work. That's different from saying people will never reach the Jovian system. A crew might one day live far from the worst radiation, perhaps near Callisto. They might supervise missions, repair equipment, study samples, and make decisions without waiting for instructions from Earth. Human presence could become possible, while direct human access remains rare. You can think of an underwater research ship. The scientists are there, close to what they study, but they don't spend every hour outside in the deepest water. Machines go where pressure makes a human visit difficult, expensive, and brief. The people remain part of the expedition. They simply aren't the part placed in greatest danger. Jupiter may force a similar division of labor. The humans stay where shielding and distance give them a workable home. Robotic craft move inward. They cross the harsher regions, orbit the moons, inspect the ice, and return data or samples. If a machine fails, the loss is painful. If a crew is exposed, the whole mission can become a rescue. So never doesn't have to mean nobody ever goes. A carefully protected astronaut might visit a dangerous moon for a short task. Better shielding could widen that window. Faster vehicles could reduce exposure during some parts of the trip. Medicine may also change what crews can tolerate. We shouldn't turn today's engineering limits into eternal rules. But those improvements don't make the human body the best instrument for every destination. Bodies need air, water, food, temperature control, waste systems, living space and protection. Every layer adds mass, every backup adds more. Then the spacecraft needs enough power and propulsion to move all of it through Jupiter's system. A robot has needs too, of course. Radiation can damage electronics. Cold can stiffen mechanisms. Communication delays still shape operations. Yet a machine doesn't develop cancer years after the mission. It doesn't need sleep, privacy, or an emergency ride home. That sounds slightly unfair after we've made the trip. But Jupiter has no obligation to reward attendance. The likely boundary, then, isn't between exploration and no exploration. It's between places where humans can live and places where humans should routinely put their bodies. We may become very good at working near Jupiter without making its most dangerous regions ordinary human workplaces. That would still count as a human achievement. A geologist directing a robotic explorer from Callisto isn't absent from the work. Neither is the engineer who designed the instruments or the crew member who handles a returned sample. Human hands don't have to touch every surface for human curiosity to reach it. This gives never a narrower meaning in practice. It may mean that people never become the main explorers deep inside Jupiter's radiation belts. The frontier could belong to human judgment at a distance, joined to machines that take the physical risk. And if machines lead the work there, what would they need to do on the moons humans may never safely walk upon? A crew near Jupiter might spend most of its working day indoors, watching images from places no person could safely visit. The machines would be down in the radiation. The people would stay behind water, metal, rock, and distance. That can feel like a lesser kind of exploration. We're used to explorers standing closest to danger. Boots cross the ground, gloved hands collect the rock. A face appears beside the machine. Around Jupiter, that arrangement may cost too much. The human presence would move outward. A base might sit beneath Callisto's surface, where Jupiter's radiation is far weaker than it is near Europa. Crews there could control robotic spacecraft with much less delay than operators on Earth. A radio command from Earth takes about 33 to 53 minutes to reach Jupiter. That's roughly the same number of minutes in either unit system, since time is unusually cooperative. The reply takes just as long. From Callisto, commands sent toward the inner moons would arrive in seconds. That changes the work. If a rover slips on broken ice, a nearby operator might react before the rover settles. If a drill jams, the crew could test another movement without waiting through an hour or more of radio delay. The machine would still need some independence. It just wouldn't be alone for so long. Close to Jupiter, those machines would need unusual patience. Radiation can damage computer memory and electronics. Charged particles can create false signals, scramble data, or slowly weaken hardware. Spacecraft already use shielded parts and systems that detect errors. Future robots might carry several copies of critical computers, compare their answers, and isolate damaged sections before one mistake spreads. Some machines could work where landing isn't possible. Balloons or aircraft might enter Jupiter's upper atmosphere and ride its winds. They wouldn't descend forever. Rising pressure and heat would eventually crush or disable them. Their work would be brief: sample the gas, measure the storms, and send the results to a safer craft above. Other robots might cross Europa's surface, where radiation is severe. A rover could move between shielded shelters. A lander might bury sensitive parts beneath ice, or carry instruments expected to fail one at a time. There's something mildly absurd about sending an expensive robot somewhere you expect it to break. But planned failure can still produce good science. The machine only has to last long enough. Humans would remain responsible for choices the machines couldn't settle well. Which crack deserves another look? Is an odd reading contamination, damaged equipment, or something new? Should a probe spend its remaining power on one more sample? You can program rules for those choices. You can't predict every strange thing Jupiter might put in front of the instruments. So people may live near Jupiter, just not where older stories placed them. Crews could remain at the edge of the harshest region. Robots would enter it, return data, and perhaps carry samples back to protected laboratories. Exploration would become a partnership between vulnerable bodies and machines built to accept the damage. What disappears is the old belief that a human body must occupy the most dangerous place for the work to count as human. The risk may belong to the machine. The judgment, patience, and discovery would still belong to us. Once we accept that change, how much of Jupiter's hidden system could people explore without placing a single boot inside its most dangerous regions? Jupiter once seemed to mark the point where human travel stopped making sense. It was too distant, too cold, and surrounded by radiation strong enough to damage both people and machines. None of that has gone away, yet the boundary now looks less like a wall and more like a problem with several possible routes through it. We've learned that reaching Jupiter wouldn't mean charging straight toward the planet. A crew could work from safer ground farther out, using distance as part of its shielding. Robots could enter the harsher regions. Instruments could watch the weather, map radiation, and inspect the moons before anyone risked going closer. Human presence there may begin at the edge, not at the center. That sounds cautious because it is. Jupiter's system gives us little room for casual mistakes. A failed part can't be replaced by the next supply ship. Communication with Earth takes many minutes each way. Even a small repair may have to wait for the right orbit, the right light, or a drop in radiation. At home, a delay is annoying. Out there, delay becomes part of the engineering. And still, this isn't the same as saying people can never go. We already build spacecraft that survive years beyond Mars. We know how to place heavy shielding around small living spaces. We can let water, food, fuel, and equipment absorb radiation before it reaches a crew. None of these methods solves the whole trip. Together, they begin to make the trip less absurd. The first people near Jupiter would probably live inside layers of machinery, supplies, and careful planning. Their habitat might feel closer to a submarine than a spacious science fiction station. Every kilogram would have a second job. Water would be something to drink, recycle, and stack around the sleeping area. A storage wall could also be a radiation barrier. Even the groceries would help protect the crew. Their greatest tool, though, may simply be where they choose to stay. Jupiter's danger changes sharply across its system. Some paths pass through intense radiation, others remain much gentler. Some moons are poor places for people but excellent targets for robotic explorers. A distant moon can offer a steadier base while smaller craft travel inward. In that arrangement, safety comes from geography before it comes from clever hardware. We don't yet know which engines, habitats, or medical protections would carry a crew that far. We don't know how people would handle years away from Earth, or whether the cost would ever win public support. Those are real limits. They shouldn't be softened into a promise. But Jupiter no longer has to mean the end of human reach. It may become the place where we learn to live far from Earth without pretending danger has disappeared. Not beside the clouds, and not deep inside the strongest radiation. Farther out, with time, shielding, robots, and distance doing their quiet work. The frontier moves that way sometimes. It doesn't leap to the most dramatic destination. It settles first where people can remain, repair what breaks, and wake up safely the next day. Around Jupiter, that safer place may be much farther out than the planet itself, and that still counts as being there.